Okay, good evening. This is Professor David J. De Los Reyes. Okay, the date for today is November 17, 2023. The time is almost 7 o'clock p.m. Okay, my topic for tonight will be a continuation of my AC machines, that is the study of alternator. And for tonight, I will be discussing example problems on alternator. Okay, let's proceed. The subject matter for tonight will be AC machines, lesson number 59, and the title of the topic will be alternator example problems. The previous last two lessons, I discussed the concept of alternator and I derived the formulas needed and the so-called voltage generation of an alternator, including all the parameters that affects the value of the so-called generated voltage. So for tonight, I will be discussing example problems on the application of those derived formulas for alternators. Okay, let's proceed. I will be giving three example problems for tonight. Example number one. I will try to read the problem. A 36-pole alternator is operated at 200 revolutions per minute. What is the frequency generated? The frequency in our houses in which we are using, like here in the USA, the frequency of the utility line is actually 60 hertz. So whether we like it or not, this 60 hertz actually emanates from the alternator side, from the power generation side, like in the hydroelectric plant, nuclear power plant, wind turbine plant. The frequency of the alternators operating there is actually 60 hertz. Okay? So at least we now know how come our frequency at our houses is 60 hertz. This emanates from the alternator side. Okay? It will be transferred to the transmission line through the distribution transformers, and from the distribution transformers it will go to our houses and businesses. So whatever frequency on the alternator side will be the same frequency arriving at our houses. Okay, let's proceed. The 36-pole alternator is operated at 200 RPM. What is the frequency generated? Given. Small letter p represents the total number of poles in any alternator. Number of poles. Number of poles meaning what do you call this? The so-called origination of the magnetic field that is being cut by the rotating winding. Okay, so the number of poles is 36. So just to give you an overview, the figure will be something like this. I have shown you how many poles here. 1, 2, 3, 4, 5, 6. No, 3, 6. We got what I place here is 8-pole generator, right? But for the given problem, the total number of poles is 36. Okay? So it's a big alternator. It's a big alternator. The one producing the flux contains 36 poles. So there are lots of flux, okay, being cut by the rotating armature. So if there are lots of flux, and there should be lots of number of turns, of course the generated voltage should be big. Because the factors handling the value of the so-called generated voltage is the total number of turns and how big the flux may be. So for the given problem, the number of poles is 36. Capital letter N is 200 revolutions per minute. For big alternators, they don't usually operate at high speed because they are big, right? They are big. It's just like the wind turbine you are seeing in the mountains, right? Or hilltops. The wind turbines actually don't rotate as fast as the so-called alternator for cars, because the what you call this, the RPM for wind turbines or big alternators is not so much, because they are big already, you know. They are big. Because if they try to operate at high speed, there will be too much vibration, okay, and it's hard to design the machine foundation for that one. So actually, if an alternator contains many number of poles and it's a very big one, actually they operate at a slow speed. Okay. Anyway, the flux is too much. The total number of turns that cuts the flux is too much. So supposed to be the generated voltage speed. We don't have to what you call this, maximize the RPM, because if we try to maximize the RPM, it's very dangerous. So for the given problem, the number of poles is 36. The RPM is 200. The problem is just asking what will be the frequency generated. Okay. This is where our frequency at our houses emanates. It came from the so-called alternator side on the power generation side. To bring out the solution, okay, to bring out the frequency, we bring out the formula on how to compute for the frequency. And one of the formulas under alternator is this one here. RPM of the alternator should be the product 120 times F over number of poles. So the only parameter, okay, that controls the speed of the alternator is the frequency and the number of poles. If you try to lessen the number of poles, okay, the RPM will be higher, right? And if you try to increase this one, the RPM should be slower, because the number of poles is inversely proportional to the number of RPM. If the number of poles is not so much, the RPM will be very fast. If the number of poles will be not, what do you call this, a little bit higher, of course the RPM will be slower. So in here, to compute for the required frequency, we are given the RPM, we are given the number of poles, so we could compute for the frequency. That's why formula is actually very important. That's why we discuss first the concepts of the alternator operation plus the so-called derivation of the formulas needed. So we will know where those formulas are coming from. So if we try to compute for frequency here, it should be the product N times P all over 120. We are given the RPM, we are given the number of poles. This 120 here is just a constant 120 coming from the derivation. So if we try to substitute 200 times 36 over 120, what will come out will be 60 Hz. That will be our answer. So for this alternator here, which contains 36 poles, okay, and the RPM is just 200 RPM, if it will try to rotate at that speed, okay, the power line frequency, the voltage generated should have a frequency of 60 Hz. Meaning, this will go 60 times per second. This is 60 Hz. Alternating current. This is time and this is E. Okay, that's why our power source, if it's coming from the utility line, it's an alternating current source, in which the frequency is 60 Hz. So at least we now know where that 60 Hz came from. It emanates from the alternator side. It's actually the frequency of the power alternator. Right? Okay, example number 2. Example number 2 is a little bit not so complicated, but it involves the formula on how to compute for the generated voltage of an alternator. Okay, I will try to read the problem. Calculate the average voltage generated in a 6-turn pole pitch coil of a 25 cycle alternator if the flux per pole is 7.2 times 10 to the 5 Maxwell's. So in here, the total number of turns. For the voltage generation, capital letter N represents the total number of turns. On the first formula, the capital letter N is actually the RPM. But actually, we could replace this one so they will not be equal by just simply capital letter T, total number of turns. So we'll replace this by capital letter T, total number of turns. So we will not interchange this RPM pair by the total number of turns. So for the given problem, the total number of turns per coil is 6 turns. So we got a coil here, 6 turns. Okay, the problem is asking what will be the average voltage generated, and this is a coil. Okay, it contains 6 turns. The problem is asking what will be if we try to expose this to a magnetic flux of a value 7.2 times 10 to the 5 Maxwells. What will be the generated voltage? Okay, flux is going out. We try to rotate this number of turns. Okay, the problem is asking what will be the value of the average voltage generated. Okay, frequency is given 25 Hertz. If we see 25 cycle, this is supposed to be cycles per second, or cycles per second in short is 60 Hertz. Okay, and the capital angle Greek letter P with okay, slash P, meaning flux per pole. We read this flux per pole, 7.2 times 10 to the 5 Maxwells. The problem is just asking what will be the average voltage generated. We are just given one coil, contains 6 turns, and if the frequency of the alternator is 25 Hz, what will be the average voltage generated per coil? Okay, we are just considering for the meantime one coil. So if there are 1,200 coils times the generated voltage, right? They are all connected in series, so it should be a very big voltage now going to our transmission line, okay, going to our houses. So if we try to bring out the average voltage generated, we will use a formula, and the formula will be this one. We derived this one the last time around. We derived. Okay, I give you this one. I discuss the parameters involving the generated voltage. The parameters that handles the generated voltage is the product of the frequency, the flux per pole, times the total number of turns, times 10 to the minus 8, and the unit of this is actually volts. That's why it's very important that before we could use any formula in the computation of our problems, if we know how to derive it, we derive it. So at least we know where that formula emanates. Okay, the frequency is given, the flux is given, the total number of turns is given. We are just considering one coil, right? It's not the total generated voltage. So by using this formula and substituting values, this should be frequency is 25, flux per pole is 7.2 times 10 to the 5, total number of turns. We are just given one coil, it consists of 6 turns. So this letter T here consists the total number of turns. It should be 6 times a factor 10 to the minus 8, and the unit of this will be volts. Okay. We multiply 25 times 6, that will be 4,320. So it will become 4.32 times 10 cube times 10 to the 5 times 10 to the minus 8. Okay. This one here, we will simplify this one. It will become 10 raised to 8 minus 8, or this will become 10 to the 0, and 10 to the 0 is 1. So actually, if we try to multiply this will become 1. And 4.32 times 1 will be 4.32 volts. So the average voltage generated in the given coil, which consists of 6 turns, the average, it is 4.32 volts. If we try to plot the graph of this, the abscissa will be the voltage at any instant in time, and the ordinate, and the abscissa is time, right? So if we try to graph this one, average voltage, it should be something like this. It's just like a DC value, you know. we are given an alternating voltage, but if we try to average one cycle, we remove this one, okay, then we try to take the average of this for one cycle. This value here is E average, this value. While we convert the sinusoidal first half and second half into its average, it will be something like this. So it is this. Okay. Example number 3. This will be a continuation of example number 2. What is the effective voltage if the waveform is sinusoidal in problem number 2? If the coil on problem number 2 generates a sinusoidal, meaning alternating, right? The problem is asking what will be the value of E with the subscript effective. Okay. The last time around, I discussed the relationship between effective and average, and there is a relationship designated by capital letter FF, and that FF is actually a form factor, right? And the relationship between effective and average for sinusoidal voltage, it is by the value 1.11. So if we try to get the effective voltage of this one for one cycle, it should be the form factor times the average. It is 1.11 times 0.432, so this is 4.8 volts. It is bigger. It should be something like this. The smaller one is the average, right? The smaller one. The bigger one, the one I will cross out like this, is the effective. E effective. Because effective is greater than average by a factor of 1.11, and the value of this is 4.8. So this is 4.8. The average is only 4.32. Okay. Why it seems it's just like a straight line. Okay. What do you call this? We average one complete cycle, right? We average one complete cycle. We do it like this. We remove this one. Okay. We average it. Okay. So it will be something like this if we try to take the graph. And this is E average. The bigger one will be depicted by a value of 1.11. Okay, that's it, guys. That's how we solve problems under alternators involving the formulas that was derived the last time around. Next topic, it will be a more complicated problem than this one. It will still involve formulas under alternators, but it involves a so-called distribution and pitch factor. Okay, good evening from Los Angeles. Professor David Gutierrez.